In this video, we're going to describe the magnetic field and force around a current carrying wire using a strategy known as the right hand rule. Now, to start us off, let's first talk about what magnets are, specifically here, a permanent magnet. If you have a material that is ferromagnetic, so say an iron nail could become a magnet. Now, it's not necessarily a magnet. Each one of the grains of iron, if you will, inside that iron nail has a magnetic domain. Now, each one of these domains likely is scattered. These domains are not aligned. They are like tiny magnets pointing in different directions, and those tiny magnets cancel each other out. If you have a strong enough magnetic field around that iron nail, you can get those magnetic fields to align. Each of those domains can then point in the same direction because you had a strong permanent magnet that you rubbed across it, or a strong electromagnetic field that you put the iron nail in. And you can turn that iron nail into a magnet. You've aligned those domains. With this understanding of what a permanent magnet is, our way of describing north and south makes a little bit more sense. North and south is basically the direction that the magnetic domains are pointing, and then the opposite direction of that. Because of that, we cannot cut a magnet in half. If you were, well, you can cut a magnet in half, but you can't separate the poles from each other. If you were to cut in half, you won't get a magnet that's just North Pole and just South Pole. The magnetic domains are aligned in the same way. So what you've done is you've created two smaller magnets, one with the north and the south, and the other with the north and the south. We cannot separate the poles. If somebody ever claims that they have designed a monopole magnet, don't believe them. It hasn't been possible. Now you can get clever with how you hide one of the poles, but there will always be a north and a south pole within that permanent magnet. As a review, we can describe this magnetic field using vectors, some arrows, and we're going to always have them point from north to south. So our magnetic field around this bar magnet looks something like this, emanating out of the north and into the south. And if I bend that magnet into a horseshoe shape, we still have a magnetic field that goes north to south, but now it's a smaller area for the same amount of magnetic field. So it's a denser magnetic field. We call it a magnetic flux. So you'll have a stronger field because the poles are closer together. All right, we describe this with a letter. We're going to use a symbol. We call magnetic field B. So we'll use B field to describe the magnetic field. Now it's weird to memorize, but you'll get used to it. B is the magnetic field strength. We use units when we quantify this in Tesla. In this particular video, we're not going to actually put a number to the magnetic field. We'll do that later on, but magnetic field will be measured in Tesla when we finally get to that. All right. Now, to understand fully the magnetic field that forms when electricity is at play, we need to introduce the concept of current. We will define this in a lot more detail when we get into electricity, but current is the rate at which charges move through a conductor. An electron is a charged particle. When it moves through a wire, it creates electrical current. Current is defined with a symbol of capital I and units of amperes or capital A. Now, way back when current was first defined, the convention was that it was the positive charges that are flowing. We now understand that that's not exactly true, but conventional current is locked in as the direction of positive charge. So this I, the charge per unit of time, is defined as the direction of the positive flow. We now know that it's electrons that are moving through a wire. It doesn't matter. I is going to be in the opposite direction of the electrons, as if it was protons that were flowing the entire time. So we'll basically just flip the script and say I is in the direction of opposite the electrons. For now, we're not going to worry about that specific definition. We'll deal with that later. For now, we need to know that current is something that can act in a wire and it has a direction to it. If you pass a current through a magnetic or a wire, some electrical conductor, that current creates a magnetic field surrounding the wire. If I were to place a compass around this wire with a current, that compass would start aligning itself with a magnetic field that is in concentric circles around that wire. Think of a hula hoop around it. So wherever you place that compass, it will align, basically point tangent to those curves. It will never point at the wire itself. We have a rule to describe which direction to point these, similar to how we said we always draw it north to south. Our convention is keeping that same directionality is we will basically make a thumbs up with our right hand. The thumb will point in the direction of the current, And then if you grabbed onto that wire with your thumb pointing in the direction of the current, your fingers would point in the direction of the magnetic field lines as they are wrapping around that wire. So think about as the direction they are wrapping, we can draw those field lines kind of looping around. Now, this is going to require us to draw in 3 dimensions. You could try to figure this out and draw kind of this isometric angled view, but it is very useful to us to be able to describe what would an arrow look like if it was going directly away from us or directly toward us. Now, the arrow doesn't have necessarily a width to it, so we're drawing basically a point in space to represent that arrow. It is helpful to think of this as like a standard bow and arrow. If you had a bow and arrow where the arrow is moving away from you, you would see the back of the arrow, the feathers or the fledging. That back of the arrow kind of looks like an X. So we are going to draw a vector going into the paper or into the screen or away from you as an X versus out of the paper, out of the screen, or toward you is going to be drawn as a dot. So if an arrow were coming at you, you would see the point. If it's moving away from you, you would see the feathers. So we can draw the magnetic field around this current carrying wire with a bunch of dots and X's. If you imagine yourself taking your right hand and then grabbing onto that wire, it's going to wrap around so that the dots are on the left. Your fingers are pointing out of the screen on the left, and then wrap around to go back into the screen on the right. So we draw it as X's. Here we can show the magnetic flux density. This is basically our magnetic field strength. It's the B field. It is the highest where these dots or X's are closest together, which makes sense that it is closest to the wire. The closer you are to the wire, the stronger the magnetic field surrounding that wire. So we can practice this with right hand rule number 1. Think about yourself grabbing onto the wire, pointing your thumb in the direction of the eye. This could be a good opportunity to pause the video and see if you could do it for yourself. But if I were to grab on this top left one, it would look something like this. My fingers are wrapping around something like this. It's coming out of the screen or out of the paper, or out of the board on the top, and then wrapping around, going back in on the bottom. So dots on the top, X's on the bottom, or you could draw it looping like I have here. If I have a current going to the left, I grab onto the wire pointing to the left with my thumb, and the current or the field, the magnetic field comes out of the board on the bottom, back into the board on the top, dots on the bottom, X's on the top. We already saw this example of the current going up, looks something like this, and then the current going down is exactly opposite. It is coming out of the board on the right and then back into the board on the left. So right hand rule number 1 describes the magnetic field using vectors wrapping around a wire that has a current running through it. Now, if that wire has a magnetic field, we can do some interesting things with the wire. Here, if you bend the wire, you have the same amount of magnetic field on the outside as you do on the inside. But on the inside, you have a much smaller area. So the same field, smaller area is going to concentrate that field and give you a stronger B field, stronger magnetic field on the inside of the loop. If I kept that going and I like coiled a wire and made it one loop after another, each loop adds a little bit more magnetic field because it adds more current. So here I have a wire that's wrapped around a nail. This is going to create something we call an electromagnet. So imagine here that I've taken that coil and then I've sliced it down the middle and given it a cross section. So here, these blue circles are basically seeing the interior of the wire. It's coming out, and then it would leave the screen and then come back in on this side. Coil around, leave the screen, come back in, and eventually it spirals all the way down to the bottom. Now, if I were to place my thumb grabbing onto that wire, it comes in like this and it leaves like this. But on these cross sections, you would imagine that this wire is coming in and then your thumb would be pointing at you. If that's the case, your fingers would wrap around in this counterclockwise fashion. Then that field or the current is coming around and back into the screen over here on the right, which means your thumb would be moving away from you, pointed away from you, still using your right hand. That would mean your fingers would now wrap in the clockwise direction. I could do this for each of these. I will find that it always shows up in that way. Coming out of the board on the left, back into the board on the right gives us counterclockwise and clockwise respectively. Um, Inside the coil, where we already know that the field is most concentrated, you'll notice that all of these vectors, these arrows, are pointing in the same direction. They are lining to create a stronger magnetic field right down the center. This here without a core is called a solenoid. With a core is an electromagnet. And you can see a couple other visualizations of that. showing how the density is much stronger in the middle. But you basically created a magnet for the North Pole and the South Pole where they loop around from north to south, as we saw before with the permanent magnet. There are lots of applications of electromagnets. From you might have electromagnets in a school where they are holding out the doors as an electromagnet that's constantly on and creating that magnetic attraction to the steel plate that's on the door. But then if the power gets cut, the doors swing shut because that electromagnet's not there to hold it anymore. We also have applications in cooler, like new forms of transportation, like a magnetic levitation train or a roller coaster that gives you a propulsion start using electromagnets. These white bars at the top are electromagnets that are attracting and repelling at just the right moments so that that roller coaster goes from 0 to 60 in a couple of seconds. All right, that leads us to right hand rule number 2. Right hand rule number 1 is basically showing that if you have a wire with a current, a magnetic field forms around that wire. Well, if that wire becomes a magnet and you place that magnet inside of a magnetic field, you're going to get an interaction between the two that results in a force. To know the direction of that force, we're going to utilize right hand rule number 2 as shown here. If you have a flat palm with your right hand, your thumb will point in the direction of the current, your fingers will point in the direction of the magnetic field. That is the same as the first right hand rule. The only difference is we're not going to wrap around. Instead, you're going to keep your hand flat and your palm is going to push in the direction of the force. I've drawn it here as a dot, showing that it is coming out of the screen at us. The palm just pushes in whatever direction the magnet is pushing. That magnetic field is creating a force. I think it's easiest to see this in a couple examples. For each of these, since my video might not align exactly with how you're seeing it, I'm going to insert a picture of my hand or a hand to show how you would align your hand with right hand rule number 2. If I have a wire here with a current I, it creates its own magnetic field. But if we know that whatever that current is produces an upward force, there must be another external magnetic field creating that force. I want to know the direction of that magnetic field. So the only way I can align my hand with a flat palm so that my thumb is pointing to the right and my palm is pushing with a force up is like this. Um, if that's the case, my fingers are the magnetic field. So my fingers are pointing away from me or into the screen. The way we draw a vector away from you or into the screen is a bunch of X's. So my magnetic field B is showing us a bunch of X's because that's the direction of my fingers. If I have a situation here where I have a current carrying wire where the current is going to the right and the magnetic field is pointing up, my thumb has to point to the right, that's I, and my fingers, the field, have to point up, that's B. The only way to align a right hand to do that is something like this. The palm is pushing in the direction of the force. This palm is facing us, so that'd be like a face palm situation where it is pushing toward us. We're going to draw that as a dot and label it F as our force. And then this last example, we have a magnetic field that we don't know how it is set up, but we do know that this current carrying wire pointing to the right has a force, which is represented with an X. So that force is actually creating a force away from us. The way that we can orient our hand is a little harder to do physically with our hand. I can show a picture though pretty easily, where the thumb is pointing to the right and the palm is pushing away from us. You'll notice that the fingers are aligned downward, which means the magnetic field is pointing down to create that force as shown. We can also show this in the case of a horseshoe magnet. Here, the only difference is we have to define the direction of the magnetic field. You remember that the magnetic field always points from north to south. So I'm going to draw in my B field here with these purple vectors. Now, if I had a wire that was going through this horseshoe magnet with a current kind of moving through the horseshoe magnet away from us, just shown in this angled view, I could represent that basically the current is moving away from us and my fingers are going from north to south or right to left. In this case, my palm is pushing up. So a wire like this is actually going to result in an upward force once that current is turned on, and the force will be up. If I switch this and then create a current in the opposite direction, my field is still north to south, right to left, but now my thumb is pointing at me, which then flips my palm to be pushing down, and that force results in a downward force. This is the general idea behind a speaker. A speaker is just a cone connected to a coil of wire that is embedded inside of a magnet. But each side of this has a north and a south kind of embedding around that coil. If I've got a bunch of currents here represented with dots that are moving toward me, I can get a magnetic field going from north to south where the dots are toward me. That's my current on my thumb that pushes down. If I flip the current, it would then push up. And a speaker is just switching the current really fast to match the frequency of the sound that it's producing to basically make this coil vibrate to push air that eventually gets to our ears so we can interpret that as sound. If we want to use the same principle to design a motor, we can do that. Here we've got a magnetic field going from north to south as we saw before, but now we've created a coil of wire inside that magnet where one side of that coil is going in and then the other side is coming out. So one side is my thumb pointing away, but my fingers going north to south, putting an upward force. And the other side, I've just flipped my thumb, so now it's going down. This is going to cause the entire wire to spin, and we can create rotation using the same principle. So we're not just jumping a wire back and forth, we're causing a coil to spin. Anytime you have an electric current passing through a magnetic field, you're going to get motion, whether it's this bouncing wire or a spinning coil. That motion can be captured and used. We call this an electric motor. Electric motors convert electricity into motion, but an electric motor can also flip it back and take motion and turn it into electricity. So it's kind of two sides of one coin. If I create that motion, basically I am spinning a wire or spinning a magnet around a wire. So a wire is moving relative to a magnetic field and inducing this electricity out the other side. Some examples of this, these are some simple illustrations of a very simple electric motor. There are some other things that happen so that the wires can switch their polarity and go positive or negative um, and they keep spinning. But we're not going to worry as much about that. We're just going to say that the current produces motion. All right, the last piece is we're going to take the wire away and look at these charges as just individual charges that are moving through a magnetic field. As a reminder, current is defined as the direction of positive flow. So annoyingly, if the electrons are moving to the right, the current is defined as going to the left. But it means that if we have a single positive photon or a positive particle, if it's moving to the right, we just say, okay, the current is going to the right. It is in the same direction as the positive. But if the particle that is moving to the right is negative, we have to flip the current and say that the conventional current, I, is pointing to the left. Why that matters is we've defined thumb as the direction in the direction of the current, and that is conventional current. So we have to take that into account if the particle that's moving is a negatively charged particle. So what this looks like is really four possible scenarios from this orientation of a magnetic field into or out of the screen. There are other possibilities. You could have it moving up or moving down. But here we have a positive proton or an alpha particle or some positive particle moving to the right. If it's moving to the right and it's positive, we orient our hand where the thumb is pointing to the right. Now the magnetic field here is out of the screen. It's drawn as a bunch of dots. So my fingers are pointing out at me. And if this is the case, my palm is pushing down. So while that is trying to move to the right, there is a force down causing it to deflect. It's bending its motion downward. This is a relatively fast particle. If it was moving slower, we would see that the curve would be more dramatic because it would have more time in that magnetic field to experience more force and cause that deflection. You can also think of it as the particle itself having momentum. And if it has a greater momentum, it doesn't change as easily, and you will see it reflect a little bit less. If I change the magnetic field to make it go into the screen, my hand just flips so that the thumb is still pointing to the right because that's the positive direction. And now my fingers are pointing away from me, causing the upward force where my palm is pushing up. If I'm going to do this for the negative charges, all I do is the same idea, just flip my hand so that the thumb is pointing opposite the electron, but my fingers are still pointing out of the screen. That doesn't change. Now my palm is pushing up, and I see that deflection upward. If the magnetic field is going into the screen, my thumb still has to point to the left, but now my fingers are moving away, and that causes this downward deflection. There are some other right hand rules that are actually a left hand rule called like Fleming's left hand rule, where it uses your left hand for electrons. If that is helpful to you, you can, or you can just remember this idea of the thumb being the direction of positive charge. So if it's a negative, you just point your thumb in the opposite direction. So that's a lot of information from the right hand rule. You should be able to describe how permanent magnets are created by aligning magnetic domains. But then the rest was using the right hand rule. Right hand rule number one was drawing the magnetic field around a current carrying wire. So one wire producing its own magnetic field. And then right hand rule number two is predicting the direction of the forces of a current carrying wire going through a pre existing magnetic field. So the magnets are interacting for a wire or for a charged particle moving through a magnetic field and how it would deflect as it's moving through.